So at this point, I'd like to go ahead and demonstrate some crashes for you. We'll go ahead and pick up some real-world examples, and we'll start out with a stop 19, which is a bad pool header. We'll then go into an NTFS file system bug check, followed by a stop 7F, which is an unexpected kernel mode trap, and we'll finish up with a stop D1, or a driver IRQL not less or equal. So let's go ahead and take a look at that bad pool header bug check. I'm going to go ahead and bring up the Windows debugger, and we're going to use the File pull-down menu to open a crash dump. As you can see, I've already browsed down to my demos. In Module 1, we have crash dump number 1 that we're going to take a look at. So bringing it into the debugger, a lot of information quickly scrolled by, so we're going to go back up to the top where we got into the debugger. As you can see, it tells us a lot of good information, like the version of the debugger we're using. It tells us the location of the memory dump we're analyzing. It tells us the version of Windows kernel. This is a Windows 8 kernel. Happens to be build number 9200 with 4 processors. So a lot of good information up here. It's the time of the system that crashed was January 2nd on 2014. The system had been up for 23 days before it crashed. Then it goes ahead and loads some symbols, and then it tells us, it says use bang analyze-v, and it's underlined. It is a hyperlink to get more detailed debugging information. We could see here it was a bug check 19, or a stop 19, and look at this. It's gone so far as to say that it was probably caused by this particular device driver, MXG2HDO64.sys. Now you'll also notice that it did give us an error, module loaded complete, but symbols could not be loaded for that particular driver. And that's because third-party device drivers typically do not provide symbols with their driver. Microsoft does provide symbols for the kernel and all of their device drivers. That's why it's important to get your symbol path set up properly before you start analyzing a crash. So what we'll go ahead and do is just bring up the help on a stop 19, because that's a good place to start, as I mentioned. So here we have bug checks under blue screens. Pull up the bug check code reference, and here we have the bad pool header bug check. So we can read about this bug check. It's got indicates that a pool header is corrupt, so something corrupted it, and then it gives us an idea of what the different parameters to the stop code are. Parameter 1, 2, 3, and 4. So again, you'll want to go through reading this information about whatever bug check you encountered to give you some background and perhaps what to check and what to look for and the different causes that may have brought about this bug check. So let's go ahead and get into the crash. We're going to start out with, as I mentioned, by using the bang analyze-v command to get more information about it. Now, a lot of information is going to go scrolling by, so let's go ahead and see where we started this command. Here we are. Here's the bang analyze-v command that we issued. And it tells us that we've got a bad pool header. The pool is already corrupt at the time of the current request. So anytime we have memory corruption, they're typically very tough to track down who done it, because by the time the driver that corrupted memory pool is executed, it's already out of the story by the time the driver that gets caught trying to access the corrupt memory pool. So it can be very tricky to debug. In any event, it gives us a lot of information about the bug check type. So we'll just briefly scroll down and look at some of this. We can see here what type of processor or what type of server it was. We can see that it was a Windows 8 driver type fault. And we'll keep scrolling down here, and as you can see, it gives you the stack text, which if we scroll all the way over here to the right side of the screen, this is the stack trace that was occurring at the time of the crash. Then it gives us some more information like the follow-up instruction pointer. That's the IP. That's what was executing at the time of the failure in this MX driver. So it gives us quite a bit of information, but what we'll do is just sort of show you a few commands that you can use to go about your analysis. Now I can use the vir target command just to show me, yes, it was a Windows 8 operating system, and there's again is the time of the crash, the debug session time. We can then do things like bang sysinfo, giving it the machine ID. That'll tell us essentially what type of server or what type of desktop or laptop crashed. We can then issue a few commands like bang thread. This shows us information about the thread that was currently executing at the time of the crash. Now if I scroll back up a little bit, we can see here that the thread was actually the CSRSS thread. And it was executing, and what we'll do is we'll take a look at the stack in a more terse fashion, because here's the stack over here on the far right. So I can issue the command just KC. That's showing me the stack in a very clear fashion. So as you may know, we always read the stack from the bottom up. So here we could see the thread executed a system service which called the Win32k.sys driver, which is part of the NT kernel. The Win32k driver is responsible for your video, keyboard, and mouse. You can see that driver did some activity before it finally called the DXG kernel, which is the DirectX kernel responsible for drawing stuff on the video. And it actually does quite a bit of stuff. As you can see, it's doing various video is supported commands before it finally hands off control to the graphics driver, the MXG2HD064.sys. It was finally that driver that was executing before it finally tried to free up some pool and ran across the corrupt memory pool, and that's why the system bug checked. So we're looking very, very closely at this one particular driver here, because that was the last one to be involved before the system crashed. Now there's different variants of the K command. We just saw the KC command. You can also do the K command by itself, which gives you a bit more information, such as the child stack pointer and the return address. But again, it shows you the same basic flow, and that ultimately we left off executing in the MX driver before we tried to free the pool and bug check. There's a variety of other K commands like the KB command, which gives you more information, and the KV gives you the most information, so much that it scrolls right the way off the screen. But to the far right, once again, you'll see the stack trace, which is important because it shows you the series of functions that were executing just prior to the bug check. Okay, so at this point we could look around and see if anything else was running out there on the different CPUs. I'm going to do the bang running dash IT command. Let's see here. I'll scroll up to where it started. Okay, so bang running -IT is the command I issued, and for each CPU on the system it's going to show what it was executing. So CPU 0 was executing the idle loop. The idle loop is executed anytime we don't have a thread ready to run. So CPU 0 was idle. Here we can see CPU 1 was also idle. CPU 2 was idle. So the only CPU 3, that was doing anything was trying to access memory pool, and that's ultimately where the corruption was detected. So we've got a pretty good confidence that this particular driver here was the only one executing at the time, and it is probably responsible for the memory pool being corrupt. So at this point, we'd probably want to get more information about that device driver, so I'm going to use the bang LMI command and give it the name of that driver. And it gives us lots of good information, such the timestamp of that driver, and we can actually see some of the build information, that it was for the G200EH video adapter. So what we would want to do perhaps is get even a little bit more information about that driver with the lmvm command. Then we would go off perhaps into the drivers folder in System32 and see who the vendor of that particular driver is, and do they have an update. You may want to contact first the vendor of the server or the desktop or laptop, because often they recommend a particular version of the video driver on those machines. So we can finish up the command lmtn or nt, and it'll show you all the drivers that are installed. I'm scrolling back up now, and you can see that there's many drivers that are all installed. And you'll notice that a lot of them have a similar date, like July 25th, 2012. Many of them have that date. Here's another one, July 25th, 2012. Well, when Microsoft releases a version of the operating system, they will essentially timestamp all the drivers with a particular date and time. That way you know which ones are present as a result of the release of the operating system, and those that have been perhaps upgraded since then. See, here we've got a driver from May 31st, 2013. That's the NT kernel. So this system has obviously had the NT kernel updated since the version 2012 was released. So to sort of summarize this crash, we've got a bad pool header, something has corrupted memory, we've looked at the stack, there's only one driver that's really out of the ordinary, which is this video driver that we focused in on. So again, I would try and find the most up-to-date video driver that would potentially fix this problem. If that didn't turn up anything positive, what we would want to do is maybe bring up, there's a tool called the verifier, the driver verifier, and I can turn on a lot more pool checking and potentially catch the driver responsible for the corrupt pool. You would do that with verifier and say standard and maybe /all. That will turn on a bunch of extra switches. Here we can see that it's going to turn on special checking flags for like the special pool, forced IRQL checking, pool tracking, etc. And more likely than not, this will catch the device driver that is corrupting memory pool. You can see here it says that a system reboot is required for the changes to take effect. You can always turn off the driver verifier by just doing a verifier/reset. So that's how I would go about tackling a Stop 19 bad pool header bug check.